16.7 Surface integrals. Last time we learned how to parameterize a surface, say using parameter u and v, and then we learned that if you take the cross product of u and v, ru and rv, you will get a vector that represent du dv here, then represent the surface element times the normal direction. So if we plot it, then this is the surface, and that is the normal direction, and this is the two vectors ru and rv. So if you want to integrate, say, a function xyz over the surface, then you can replace this xyz all by u and v. So you will have x as a function of uv, y as a function of uv, z as a function of uv. Then you have this thing here, the norm of ru cross rv, then du dv, because the norm of this will give you the norm of that. So that's how you find out the integration in a general setting. It could be complicated because this ru and rv are two vectors, and when you find the inner product, cross products, then take the norm. However, we are mostly interested only in three special cases. Case 1, the surface is given as z as a function of x and y. So Rx is just 1, 0, Zx, and Ry equals 0, 1, Zy. And if you take the cross product, you will see it's negative Zx, negative Zy, and a 1. So if you take the norm, then it's the usual square root formula we know. Second case, we are talking about a cylindrical surface. Alright, so suppose you have a point here, and this is, by the way, when we say cylindrical surface, we mean this r is a constant. So the parameterization is in theta and z, not in r, because r is fixed. Then this is r theta, and this is rz. So r theta, well, what is r? R equals r cosine theta, r sine theta, and z. Remember, r is fixed, it's not a parameter. So r theta equals negative r sine theta, r cosine theta, and 0. And rz is just the k vector. So if you do that, r theta times rz, you will see, because this one is pretty simple, it will be just r times n vector. And this n vector is a unit vector. It's just this cosine theta, sine theta, and 0. And then you can see that using the visualization here. So you see r theta is perpendicular to rz, and if you take the inner product, it will be just point outward horizontally. So this is the direction of n, right? Which is just that. And the norm is just r, because then you write on, when you write on the integral, let's say f times ds over the cylindrical surface, right? Then you will just write on this as a f times r d theta dv. And this r d theta is what we remember the old formula. It was like this: r d theta dz, right? But that's for the volume. Now there is no dr because it's only the surface, so we only have the r d theta part. Okay, so remember this formula. Okay, and n is just that. And third case is a sphere. Say you have a point here. This is a r theta, and the r phi is going down, right? So r theta, r phi, if you take the cross product, you will get this n direction. So we did that before. Suppose the radius is r, capital R, which is also a constant, and r equals r sine phi cosine theta, r sine phi sine theta, and r cosine phi. Right, and if you take the cross product, r phi with r theta, after some calculation, it can be shown that it's a number which is r squared sine phi times the n. And this is just a factor in front of the d phi d theta. And this n is nothing but the radial direction. In this case would be just sine phi cosine theta, sine phi sine theta, and cosine phi. Alright, it's just r divided by capital R. So we can see that when you do the integral, f times ds, if this is spherical surface, right, then this would be f times just this part, r squared sine phi times d phi d theta. And once again, we have seen this r squared times sine phi in the volume integral. It's the same thing, except there is no dr because, it's a sphere. It's only a 2D surface. Alright, so this is another formula that we will use. Now let's go to the integral over surface, and let's see some examples. The first one is a corner piece. Say you have x, y, z, and you have a point 1 here, 2 there, 3 on the z-axis, and you connect them. This is 2. And then you get a triangle, right? So let's find out the integration over this triangle. This triangle here, we call it S. And then let's integrate a function, let's say xz. Okay, so you can say this is the density of this triangular piece, and you find out mass, for example. So how do we do that? Well, you need to write down an equation for this surface. This is a plane, and the easiest way to write down the equation is this: x over 1 plus y over 2 plus z over 3 equals 1. Because then you can determine the intercept by plugging, for example, y equals 0, z equals 0, and x equals 1 is here. Then for y you get 2, and for z you get 3, right? So we can solve for z. So what is z? Z equals 3 times 1 minus x minus y over 2. Right, because you can move x, y to the right hand side, then times 3. Alright, then what is this integral? We will choose x, z, then this is 1 plus zx square, zy square, and dx dy. Okay, what is the domain in xy? You can see is x, it's 1, that's 2, that's y. Right, so x is between, or the way I wrote, I have a x inside. So y is between 0 and 2, right? 0 to 2. And x over 1 plus y over 2 equals 0. No, equal to 1. So what is y? Y equals 2 times 1 minus x. So, well, since I have this equation, how about we switch them? So let me switch x and y. So let's first do y, then do x. So x is from 0 to 1, and y is from 0 to 2 times 1 minus x. Okay, so for every x, y is from 0 to the right hand. Okay, so let's integrate. Well, before that, we have to do one thing. You have to change z, right? Because you cannot have a z there. What is z? Okay, z is here. So it's x times 3 times 1 minus x minus y over 2. Then what's inside of the square root? 1 plus, it's here. So take its x derivative, you get negative 3. And take y derivative, you get a negative 3 half. Alright, so inside integral, you have 10 plus 9 fourths. So 10 plus 9 fourths, and that's 49 over 4, so 7 over 2 if you take a square root, and that's 7 over 2. Alright, so we get 7 half, 0 to 1, and inside integral you have you have a 3 out there, so you can times 3, so it becomes times 3 here. Then you get this integral, x minus x squared minus x y over 2 dy dx. Right? And you have 21 over 2, 0 to 1. Then you have x minus x squared times y minus x times y squared over 4. And then you plug in 0 to that. Then integrate over x. Alright, then 21 over 2. And then you get 0, 1. You get x minus x squared 2 times 1 minus x minus x over 4. Well, this 4 will be cancelled, right? Then you get 1 minus x squared. That looks good. Alright, let's see. That's good because this equals x times 1 minus x, right? So you have 2x 1 minus x squared minus x times 1 minus x squared, so it's cancelled. So equals 21 over 2. You only have one of them left. You get x times 1 minus x squared, right? And that's pretty good. So you get 21 over 2. Then you get x minus 2x squared plus x cubed. Right? Almost done. So 21 over 2. Then x gives you 1 half. Then plug in 1. Then 2 over 3. Then plus 1 over 4. And that's it. So what is it? This is 1/6. Right? Oh, this is negative 1/6. So then you have 1/4 minus that, 1/12. So it's 21 over 24, which is 7 over 8. Okay, the answer is 7 over 8. Right, that's the integral of xz over this triangle. Yeah, it makes sense. It's, this triangle not very big. So I hope it's correct. Alright, now let's see second example. Second example is a sphere. It's a semisphere actually. So let's find out let's say find out the integral over the hemisphere x squared plus y squared plus z squared is equals 4. And z is greater than equal to 0. So it's the upper hemisphere of radius 2. Let's find out the integral of x squared. Okay, since it's a sphere, we should use the spherical, well, in this case, not really spherical, it's just a theta and a phi, and no r, because r is fixed. Okay, and the limit is pretty easy. Theta is from 0 to 2 pi, the phi is from 0 to pi over 2, right, because only the upper half. And do you remember this thing here? R squared sine phi. Right? It's just the 3D thing without the r. So what is x? Well, x is not so simple. X is r times sine phi cosine theta. Right? Alright, let's continue. So we have this r squared times r squared, so we get r to the 4th, which is constant. Then you have, for theta, you have cosine theta squared. And for phi, you have this sine phi cubed, right? Okay, so continue. And the cosine theta squared, how do you do that? 1 plus cosine 2 theta, right? And how do you do this? You can combine one of the sine theta with that, you get a d of negative cosine phi. Then you have sine square phi left, but we need to write down in terms of cosine. How do we do that? 1 minus cosine phi squared. Right? Okay, then you have r to the 4th, and this gives you theta plus sine 2 theta over 2, and plug in the limits. Pi over 2, right? And you can see pi over 2 times 2 equals pi, so this is gone. Oops, this is gone. This is pi over 2, right? Then this one will give you, so you put the negative sign here, so you get cosine square phi, you get cosine square phi over 3 minus cosine phi. Right? Then you plug in the two limits. Wait, this is pi over 2, that is not pi over 2, that's 2 pi, but it doesn't matter, it's still gone. Alright, so what do you have now? R to the 4th times this is half, so it's pi, and the last term would be, if you plug in half pi, you will get 0, then plug in 0, you get 1, so you get a 1/3 minus 1, but it's in the negative, so it's like that. So it's 2/3 times pi times r to the 4th. Alright, so that's what you have. And I believe that is correct. So alright, let's see one more example. This one will have some cylindrical part. It's a little bit complicated. This time we'll consider a 3D solid domain. It's between three surfaces. It's bounded by three surfaces. E is bounded by x squared plus y squared equals 1. And that's a cylinder. And z equals 0. That's a plane. And v equals 1 plus x. That's also a plane. So let's sketch it. Let's say this is x, this is y, sorry, this is y, this is z, this is x. So x squared plus y squared equals 1 is a square, then it's a circle and a cylinder. Z equals 0 is just xy plane. Z equals 1 plus x is like that. Right? So it's a line. But if you cut it, you will get this. Right? But it's a 3D thing. So what you get is this. This is the top surface. This is the bottom surface. And the side is cylindrical. So you get a top face, bottom face, and a side face. Right? Top and bottom are two cylinders. Sorry, are two planes, and side is a cylindrical face. So let's find out the integration over this closed surface. Put this one for closed. So that means it includes all three faces: S1, S2, and S3. So let's call this the boundary of E. Just let's say put all together, call S. Okay. And then let's integrate Z, the height. And Z is always positive, so the result is also positive. So this means you have to integrate over S1, then S2, then S3. Right? And we are kind of lucky because S2 is on XY plane, so Z equals 0. So we only need to worry about S1 and S3. Right? So let's see what is S1. S1 is a plane. And where is the plane? Plane is given by this. But to find out the integral, you have to project onto XY plane. And then you will get this circle. Right? So S1, let's find out what S1 first. So for S1, it's a Z equals 1 plus x within that. Right? So we should use the xy, and then you have a z times 1 plus zx square plus zy square dx dy, right? Or can just say dA, and this is x squared plus y squared less than equal to 1, right? And what is that? Zx equals 1, zy equals 0, so you get square root 2. And what is z? Z equals 1 plus x. And then we write on dA, since it's a circle, it's best to write on the polar coordinate, right? It's polar, not cylindrical. Okay, then r is from 0 to 1 and theta from 0 to 2 pi. Okay, and what is x? X should be written in terms of r cosine theta, right? Then you can see it's integration over r first, then times r to that, you get r squared over 2, then times that, you get r cubed over 3, and then it times cosine theta, right, from 0 to 1. So if plug in r equals 1, you get 1/2 plus 1/3 cosine theta. Alright, then cosine theta will give you sine theta, and 1/2 gives you theta from 0 to 2 pi. And once again, this guy is gone, So you just get square root 2 times pi. Okay, well, this is only half of it. We have to integrate over the S3, right? Remember that? The side. Okay, what is S3? S3 is a cylindrical surface. So how do we parameterize cylindrical surface? We should use theta and z, because this time r is fixed, right? What is r? R equals 1, right? R equals 1. So let's see, what do we do? We integrate z ds, right? So cylindrical, right? So z is just still z, and this s, if you remember, it's r d theta dz, and r is just 1. Okay. And how about the range of theta and z? Well, because this is not a real cylinder, it's a part of the cylinder. So z is depending on theta, right? What is the relation between z and theta? It's here. Z is between 0 and 1 plus x. And what is x? In this case, since r is fixed at 1, so x equals cosine theta, right? So you can see z is between 0 and 1 plus x, which means 1 plus r cosine theta, and that's 1 plus cosine theta. So z is between 0 and 1 plus cosine theta, so we'll have to switch them. You have to dz, then d theta. And theta is from 0 to 2 pi, and z is from 0 to 1 plus cosine theta. Okay, and then you can integrate. Okay. So 0 to 2 pi, and r is just 1. Z gives you z squared over 2, and plug in the 2 limits, right? Then you have 1 plus cosine theta squared over 2 d theta. So what do you get? You get, well, let's check out 1/2. Then you get 1 plus 2 cosine theta plus cosine theta squared, right? How do you do that? You write down this cosine 2 theta here. Then integrate. Okay, so you get 1/2. Then this 1 and this 1/2 will give you 3/2 theta. Then you get to 2 sine theta, and this 1/2 cosine theta will give you sine 2 theta over 2, right? And all of the sine part will be gone when you plug in the limits. So in the end, you get 2 pi divided by 2 is 3 pi over 2. Okay, let's see, what is the other part? Square root 2 times pi. Correct? Yeah, I hope so. So altogether, you will get integral equals square root 2 plus 3/2 times pi. Okay, that's it for the last example. Alright, maybe we can just take a short break and continue next time.